So I'm John Seinfeld from Caltech, and it's my pleasure to introduce the next two speakers. The first is my colleague at Caltech, Nate Lewis, who's the George Argyros Professor of Chemistry. And Nate is going to talk on artificial photosynthesis.
Perfect. Thanks very much, John. It's great to be here and share with you what we're working on. It's certainly not done. I'll just give you our thinking process and a progress report on really a project that we started in my group, really about 2.5 years ago. I also will give you an introduction to the thinking behind this, coordinated with Dan's talk next so that I will be efficient in slides as well as everything else, so Dan won't have to show the same introductory slides. I should thank DOE and NSF. BP funds our work to make solar electricity. These people in Dreyfus fund it to make fuel. I think most people are familiar with this number and set of units now, but for the people that aren't, it's always good to calibrate. If you take all the energy consumed in the world in a year and divide by the number of seconds in a year, the world's energy meter would be somewhere hovering about 15 trillion watts. It will go up. There's not been a year in the history of our planet that we've actually used significantly less energy than in any year before. In the face of economic growth and population growth, most projections of the EIA and the IEA and many other agencies believe that it'll be 25 to 35 terawatts average consumption rate within our lifetimes. And that built in business as usual assumes that we save as much energy as all the energy we currently use. Then you could hold it to double current rate. If you saved even more than that, which turns out to be down to a burden of twice the level it takes a human to eat per capita, you might hold it constant, something the world's never done. Of course, 85% of that comes from fossil energy right now. And that means that just even to meet demand, if it's going to double with aggressive conservation, you need 14 or 15 trillion watts of new energy of some kind. If your goal is to keep the glaciers from melting further and to reduce the rate of emissions by 80%, essentially 80% means reduce it all. And so if you can fill this difference by saving as much, again, energy as all the energy we consume, that means you still have to make as much clean energy as all the energy we consume within our lifetimes. That's what it takes, the arithmetic, to stabilize emissions. You can break it up into wedges on supply and demand. The arithmetic is the same. You have to make as much clean energy as all the energy we use, and you have to save as much energy as all the energy we use if you're going to hold demand double and cut emissions to essentially zero. We know what the consequences of not doing that are likely to be from the ice core data plotted with human fossil fuel emissions in the last 50 years. What's not appreciated widely, I didn't hear it today earlier, is the one number that I think is the most important number, which is the time to relax back if we stopped in 50 years at that level of CO2 back to the planet that we got from our parents at 280 or 300 parts per million. That's really characterized by two time constants. The first 3/4 of that 550 ppm delta function pulse would decay in about 400 or 500 years. The next 1/4, best knowledge says, would take 10,000 years. Nobody has a technically credible way of removing the 600 trillion pounds of CO2 that is distributed dilute in our atmosphere. If you do, you should ask Richard Branson. He'll give you $25 million on the spot. So we can say that within the next 50 years, we are going to flip the switch on the delta function laser transient experiment that's going to pulse the chemistry of our atmosphere for a timescale comparable to modern human history. Period. Seeing the ice melting, it's melting much faster than people predicted. Just as Jim said, the permafrost is melting and isotopic dating both of the helium and the methane tell us it's melting in areas it hasn't melted in 40,000 years. None of these things these positive feedbacks are really captured in any faithful way in climate models because we don't have human experience of them, so we can't extrapolate and model when they'll kick in very well. We don't know. In the Permian era, by the way, the one I like to refer to as opposed to the Eocene, when the CO2 did spike in a much more rapid time constant than the more gradual one up in the Eocene, there was a massive isotopically light release of carbon, presumably from the permafrost, that was catalyzed by some other events. We know temperature spiked 6 degrees, 8 degrees on average centigrade. And from that rapid change, similar to the one that humans are now inducing, we know from the fossil record that 90% of the species on Earth could not adapt and went extinct. We do not know this would happen again. We do know there's only one way to find out. Well, if you need about 14 trillion watts, you can get it from nuclear power. If you want to build a new plutonium-containing nuclear power plant every single day forever, because you have to build one for 40 years to make 14 trillion watts. They only last and are commissioned for 40 years. By the time you build the last one, you'll have to decommission the first one. It turns out that there is more energy in natural gas on our planet than there is in all the terrestrial uranium-235 when used in once-through cycles. So it's not even credible to think about, if this is the scale you're going to do, nuclear power without thinking about crediting the Iranians and North Koreans for stepping up to do their part to mitigate global melting, right? So 40 reactors doesn't mean anything globally, right? This is the cruel arithmetic of energy. It's 14,000 to hold CO2 to double if you save as much energy as all the energy we currently use. If you don't want to do that and want to build one a week, you leave 90% of the problem on the table. You could get it by burning fossil energy and capturing and storing it. We have no idea whether or not at scale this works technically. And actually, I think there are very important chemistry problems in the three-phase flows underneath the soil in the Earth of the migration, monitoring, prediction, and modeling of where carbon dioxide would go if we tried to bury gigatons under our soil. I'll just give you a feeling, though, of how big this is, because Steve Piccola has done a nice calculation, taking the density of supercritical CO2 at 1,000 meters, and assuming that we did do it all for 100 years, and that it didn't leak, because if 1% of it leaks after 100 years, the net flux is identical as to what we're mitigating in the first place. If none of it leaks, and you put it all down there, the United States CO2 emissions, and the CO2 were distributed uniformly across the continental United States, it would displace the surface of our continent by an average elevation of 5 centimeters. This is good if sea level rises, right? You can change Jim's pictures. This is what we mean by clean coal. Okay? Just advertising it on television doesn't mean that it works technically at scale. Even the most advocates of carbon capture and storage think you might do at most 10% of our emissions sequestered this way because of these considerations. And so if you don't get it from one of those two things, you have to get it from renewables. This is a famous numerical chart that I first generated in 2002 for an NRC study. This number is technically in good shape. Hydroelectricity is maxed out. Not much room to grow. The renewable, sustainable geothermal flux is in good shape. You can mine it faster than that, but you'll use it up just like using up coal. This is the sustainable amount because we know the temperature at the core and the diameter and thermal conductivity of the Earth, and you know the geothermal heat flux is in every textbook. So there's only 10 terawatts to be had with 100% efficient heat engines covering all the land on the Earth, forgetting about saluting to the French Sergeant Carnot. Right? This number's in good shape. There's only 2 terawatts and all the energy flows in all the oceans and tides. Wind guys are fighting back. Current thinking, and when I first did this in 2002 from several peer-reviewed sources, was that it was about 2 to 4 terawatts of extractable as electrical energy in the high wind speed areas on the Earth. They're fighting back and now saying, well, maybe there's 10, maybe. But of course, the sun couples weakly to drive all the winds. This is still an uncertain number to within a factor of a few. Biomass, if you took all the land not used for food, planted it with the fastest known growing crops, and assumed 100% conversion efficiency with no losses and no energy into the farm, you might get 5 terawatts. And that doesn't assume that you paid the carbon debt, which happens when you decrop something else. It's because photosynthesis is an inefficient machine for converting sunlight into stored energy. In fact, only 1% or less of the total sunlight over a year that hits a crop is stored, even in switchgrass and miscanthus, in all the lignocellulose and biomass of the crop. The reason that photosynthesis saturates at 1/10 of a sun to protect itself from radical damage, because it turns out rubisco is a pretty bad enzyme, and it can't turn over fast enough, so it shuts down the electron flow to prevent radical damage in the canopy at shade at about 1/10 of a sun. And because of that, and because plants have the wrong band gap, they should be black, not green, those two things conspire to make them inefficient machines. In fact, plants rebuild themselves every 30 minutes, and most of the energy in a plant is used to rebuild the plant to keep it alive. In universities, we call that overhead. But there's a big number. There's an only unequivocal big number. Famous statement, more energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Another way to think about that is in 1 year, more energy from the sun hits the Earth than all the energy consumed by humans in history. And that statement's going to be equally true 100 years from now as it is today. So it's pretty clear what you want to do. You probably can't see your way clear to holding CO2 to even double, no matter how much energy you conserve, unless you have significant amounts, maybe of wind, but certainly of sun, contributing to the energy mix. There are 3 ways we know how to do that. Nature did it for us, but inefficiently, and we wouldn't really care about a failed machinery called photosynthesis, except it figured out how to store energy in the most energy-dense form known on our planet, except for nuclear energy. It stored it in chemical bonds. So that's why we care. We can go get it later. But photosynthesis, as I said, is very inefficient. Solar cells are very efficient. They can be 20% efficient, but they make the wrong product. They make electricity. There's no good way to store massive quantities of electricity. If there is, you should just do that right now, buy electricity every day at 25 cents a kilowatt hour, at a nickel at night, sell it to everybody at 25 cents a kilowatt hour, and fund your own research foundation. Profits. Doesn't exist. You can pump water uphill. That's good in your backyard. It's good every winter and emptying it every summer, but it ain't good if you want to buffer the day-night cycle of the United States of America, because you need something like 500 lake meads filling every day and emptying every night. This is the difference between the energy density of 1 gallon of gasoline. You have to pump 55,000 gallons of water up the height of Hoover Dam to store the same amount. So we got to find a way to take sunlight and do it ourselves with the efficiency of solar cells, so we don't have the land area impacts of using an inefficient machinery, but that makes chemical fuel that we can store, because it's not enough to build an energy system that you just capture and convert sun. You have to also store it, because my little saying is that he that cannot store will not have power after 4. Johnny Cochran would be proud. Photoelectrochemistry really works. When you take semiconductors and shine light on them due to a magic charge separation property similar to what makes a transistor, this picture from Doman's lab that I borrowed, now, shows you can take light and shine it on this semiconductor and make fuel directly with no wires, just like a leaf would be doing. This makes hydrogen and oxygen from sunlight. The quantum yield of this process for wavelengths of light that is absorbed is essentially 1. Even the fact that this is not highly colored, even taking that into account, the total energy efficiency of this system that you were seeing is still greater than that of the fastest growing plant, based on an energy input from the sun divided as the denominator into the total amount of free energy produced in the fuels. So we know that birds fly, have wings, airplanes fly faster, they don't. We already know that we can make fuel from the sun better and more efficiently than nature has given us. We just don't have materials that can do it very well, because that material would have worked even better on the moon because its band gap for strontium titanate is 3.2 electron volts, so it only responds to a small fraction of the solar spectrum on Earth. There's no known single material, holy grail of photoelectrochemistry, that can absorb a lot of sunlight and last in the presence of sunlight at the same time. Probably the reason for that is that it has to both survive highly oxidizing and highly reducing environments at the same time, at two different parts of that same material. And so we were inspired, actually, by when I was visiting Francois and at Princeton in 2003, when Steve Piccola came up to me and said, "You artificial photosynthesis guys have to figure this out because there may be no other way." So the photosystem 1 and 2 inspiration of plants is, of course, they separate their products by a membrane, and they use two photosystems, not one, and they actually have a very oxidatively unstable iron-sulfur type of system that catalyzes at a soft site, the reductive process. It never sees the oxidative environment. They have a hard manganese site, the oxygen-evolving complex. It never sees the reductive site. And by separating the products, you also can separate the two different species chemically from having to react with each other. And maybe more importantly, you don't want to make hydrogen or hydrogen incipient here and oxygen in the same place at the same time, because you know what happens the instant a cloud comes over this system, goes kaboom. So the inspiration for that was to build our own. Build a membrane with the pigments not being the ones that nature used, but being more robust inorganic materials, and also couple them without wires to make chemical fuel directly in a system that I drew on a napkin in about 2003, right after I got back from Princeton, that we now have lovingly coined the term because Jonas told us to figure out something to call it, alliteratively powering the planet. What else? There was one more important design principle. The other important design principle is while we had a membrane, I thought that at the time we could have done that with a photovoltaic cell, but they're way too expensive and arguably not scalable, because crystalline materials out of things like silicon, to give you a scale equivalent, you have to put up 1 million solar roofs every day for 50 straight years to hold CO2 to double. I don't think anybody can put 1 million straight solar roofs a day with the materials we have now. You can't get to scale. So we need to find a way that can get to scale real cheaply. And one way is to think about using this structure of rods, because instead of growing a single crystal that would be brittle and would have to be very pure, if you drew things that were oriented like grass or carpet or trees toward the sun, you could then absorb light, and in this idea, you would be able to use very cheap materials and process them in a very simple way. In order to couple this two-photon system, one which would absorb the blue light and let through the red, and the other absorb the red light, and separate the hydrogen and oxygen, we need a membrane. And we also need catalysts to convert the electrons to reduce water and convert the holes to oxidize it. And we, of course, farmed the harder parts, we thought, of the problem out to Dan Nocera and Jonas Peters. Jonas has now surpassed us by having a great catalyst made of cobalt to reduce water to hydrogen, and Dan's far surpassed us to have a great catalyst to oxidize water to oxygen, which he'll tell you about. And we've still got to develop the pieces here, because if we don't make them all work together at the same time, we don't have much. Why was the nanorods important? The rods are important because planar solar cells in design from Bell Labs back in 1950s have an important physical constraint. You need 300 microns of silicon, for instance, to absorb sunlight. That's the absorption depth in silicon. Any less wastes sunlight by letting it through, any more wastes silicon. So you can grow 300 microns of a crystal of silicon, but it has to be very pure, because for the light that's absorbed very deeply, the excited state created has to last back 300 microns to get back to the space-charged region in the wires to lead to current. And it's this one law that is why all solar cells share about the same cost per watt, because the ratio between the purity needed to get the diffusion length relative to the absorption depth within a factor of 20% is the same no matter how you make it, no matter what material you make it out of. So this was an unsolved problem that we decided to change the rules, and therefore we might be able to change the solutions. The way you would change the rules is you still need 300 microns long to absorb the light, but if we want to make really cheap silicon, for instance, or other materials that have short diffusion lengths, Let's just make them go sideways only the short distance that they can go and orthogonalize their direction of collection relative to their absorption. If you change the rules, you can open up a whole new set of design principles. And that's why the rod structure was on that napkin. This radial geometry would in principle allow for a high quantum collection efficiency even for really cheap materials or non-stoichiometric materials or materials you would be crazy to use in this planar design that we are now making solar systems out of in our lab. One example is rust, where you need a few microns to absorb the light, but it's highly non-stoichiometric as hematites found in nature, highly defective, and Keras can only move 40 nanometers. So the only 40 nanometer top part is live, and the other 3 microns is just dead. So we just make 3 microns long, 40 nanometer diameter rods, and they're alive. Make them out of pyrite, fool's gold. So we're making combinations of solar active materials out of fool's gold and rust. You can decide whether we're crazy. We then did theory. A joint student with Harry Atwater and myself, Brendan Kays, did a full device transport physics theory, which we're guided by to show indeed that we know all the transport device physics of silicon and carriers in silicon, that as a function of the rod diameter, there's a sweet spot where you can have low diffusion length materials and still have high full device physics predicted efficiencies, 10, 15% efficiencies at diffusion lengths of a few microns, which is really rotten silicon. There's probably something to this design because, after all, that's what an aspen forest does. Long axis to absorb light, short axis to move the heavy, slow-moving nutrients. It's what root systems do. It's what leaves do. It's what stomata do. It's what retinal rods do. This orthogonalization principle is all throughout nature. So it seems like a good thing for us to try to exploit. The other important thing, as I alluded to, is this is what the periodic table looks like in our laboratory. It looks like a logarithmic scale of the abundance of elements in the core of in the crust of the Earth compared to silicon. And we have a line right there, and you're not allowed to go below the line. No iridium, no rhodium, no osmium, no platinum. Because if we don't have a whole lot of time, we don't have time to screw around with those elements anymore. We got to figure out something that you could make 1 million roofs a day of, and those are above this line. It's heretical for an inorganic chemist, but the important point is that there are materials like zinc phosphide, like iron sulfide, like iron oxide, that are above this line, that are earth abundant, that you would never make planar solar cells out of because they can never be made pure enough, cheaply enough, to satisfy that planar ground rule constraint. We can just change the aspect ratio of these structures and we think open them all up to work. The other important point is that the solar photon flux hitting a plane doesn't change. But if you take something like this high aspect ratio structure and decorate it with catalysts, if you make a fuel cell, you need to use platinum. It's the best catalyst out of all the known ones at all pHs, known in this volcano curve for 50 years, because you need an amp per centimeter squared. But the solar photon flux is only worth 20 milliamps per centimeter squared. And if distributed over this very high surface area, you relax the turnover number on the catalyst because it has to turn over less often since there's more area feeding the same total number of flux. And that means that if this is 3 orders of magnitude higher in surface area, you can use and satisfy the flux constraint catalysts that are 3 orders of magnitude less active than platinum, like nickel or copper or cobalt or MOS2 and so on. And so we don't need the most active catalysts in order to have low overpotentials in principle to either oxidize or reduce water. So we can stay above our line in earth abundance without having in principle to develop new catalyst systems to do that. Second advantage of these high surface area features. Okay. Now I'll tell you what we've done in the last kind of 2 years. We've been furiously working at this. We first decided to test the theory. This is an Alumina template. It's just aluminum that's oxidized to make ceramic alumina. You can electrochemically control the pore diameter by etching, current density, as well as the pore depth by how long you etch. We can do this over large areas. This is a 1 micron scale bar, and it gives you a feeling for what we can do with this template. We can then electrodeposit in those pores a material. This is a test material in this case, cadmium selenide telluride. It was just a prototypical material that we could test the theory on. because we know we can electrodeposit this. We know it's photoactive. We also know that you can't make it have a diffusion length longer than 1 micron, and you need 3 microns to absorb all the light. So in a bulk crystal or thin film, we know it's highly inefficient. So we just sputter a cadmium selenide layer there, put a metal back contact on, electrodeposit from a bath the cadmium selenide telluride in our template. The template, alumina is soluble in base. We etch it off in base. We're left with the forest of rods that are 3 microns long, but smaller than a micron in diameter, and so we should be able to collect things sideways. And then we fill this up with a liquid that's going to collect everything that can get sideways and see what we see. Here's an example of this kind of first generation photon forest. Here's a 1 micron scale bar, long enough to absorb the light, highly dense, and there's also some photon trapping and scattering in between. The key experiment here is to vary the wavelength of light. For a planar cell, as I've said, very short wavelengths are going to be absorbed strongly, and they'll be within that micron active layer and give us high current yield. But very long wavelengths of light near the band gap are going to penetrate too deeply, and the current should die. On the other hand, same material grown exactly the same way at the same time, but in the highly packed nanorod structure should have the ability to collect carriers sideways for both the short and the long wavelengths. So that's a definitive check of whether or not we're on the right track. Here's the data. You can see, in fact, that the planar structure works as advertised and reported previously in the literature. The band gap is about 800 nanometers. You only get a fraction of the photons absorbed, collected as yield, and that fraction increases up to all of them only when you get to very short wavelengths, but you lost almost all the solar spectrum photoactivity in the meantime. But the exact same material grown the exact same way in the radial morphology collects carriers from the band gap all the way through as if you had them all the time, because they only have to move within their diffusion length sideways. Okay, so that's good. So cadmium selenide telluride's below the line. For time purposes, I'm skipping a lot of work. We wanted to grow them out of silicon as the cathode side of this material. Silicon's been shown to be a good cathode in bulk form by Texas Instruments and Adam Heller. It's just that we had no way to grow it nanostructured. So we grow it from the vapor liquid solid growth catalyst method, where you can known from Wagner and Ellis in 1964, and now all the nanoscience people, like my old student Charlie Lieber, use this as ways of growing individual silicon structures. We need to grow large area arrays, so that's another non-obvious trick. We do that by either stamping or, in this case, photolithographically patterning little gold, nickel, or copper catalyst balls on a silicon wafer. And when we tried to grow structures with that, they should grow epitaxially underneath these metal catalyst particles that cracks the chlorosilane and then precipitates the crystal of silicon. The gold rides on top, and it seeds this just like growing corn, kind of like nanobio corn. Except that we got nothing. And what happens is when you grow from chlorosilane, which is a very cheap method of growing silicon, it's practiced in factories by Wacker the size of this building. And the hard part is purifying it. We're not going to purify it. We got nothing, really, because it turned out that the gold particles moved around and ripened on the surface. And when you start with that template, you've lost your initial pattern fidelity. So we added an oxide buffer layer so that these metal particles that were deposited have nowhere to go. And in fact, they retain their pattern fidelity after a test anneal. And then we crack the silicon and let it grow. And this is my favorite picture. That's what we get. This 100 micron bar. These are perfect single crystals of silicon by TEM that are 100 microns tall, 4 microns in diameter, spaced on whatever pitch we patterned them initially. A single crystal. And I know I've got 1, 2, 3 former Bell Labs people here who are ready to jump out of their seats because they know that I'm going to tell you that these are gold-saturated silicon samples at a growth temperature of 1,000 degrees, which they were told never let gold anywhere near silicon because it's a deep-level trap. And the only other option, of course, for growth is we can do it instead of with gold. We can do it with nickel or with copper. Still going to jump out of your seats. But in fact, the solubility limit of gold, nickel, and copper in silicon is even still, with a deep level trap, enough to give you a 2 nanosecond lifetime, which is a 2 micron diffusion length. And these rods are only 4 microns in diameter, and so we should be able to collect them all. Okay? So this is really rotten silicon, which we can just thermally refine and purify, but we don't need to. And indeed, works pretty well. We get about 450. This is a current voltage curve in a liquid junction of those rods. Single crystal of silicon, expensively purified under these conditions, would give us 500 millivolts open circuit. We're at 450. It would give us 30 milliamps per centimeter squared. We only get 12 now, but that's because we only fill 5% of the optical filling plane at normal incidence. We've got to do better than that. And we still have a shunt left behind. That shunt, we believe, is due to the residual gold on the side walls that we're furiously etching off right now. So in principle, this works. It's really cheap silicon grown on an inorganic substrate that works almost as well as if you grew a single crystal. But I promised you that we would be going toward this membrane. Kate Ploss and the group was inspired by John Rogers' work, and I know Ralph Nuzzo's in the back, and Ralph's, where they've used PDMS molds to make flexible electronics. PDMS, polydimethylsiloxane, known lovingly in our group as fish tank goop, because it's the stuff you buy from the hardware store, has this wonderful property that when you peel it fast, it's stiff, and when you peel it slowly, it's goopy. So we just squirt that stuff in these rods on this array, and then give it a hair peel. And off come the rods, and they only leave little stubs behind. And their orientation is completely preserved in this PDMS film. And so now we have an inorganic, filled, single crystal array of silicon rods that bridge macroscopically a bendable, processable piece of plastic. When we do this with a polymer that actually has enough monomer in it that it'll evaporate, we can control the thickness of that. And what we're left behind with is there's the polymer, there are the rods. These are all single crystals of silicon over large areas. This rolls up, you can unroll it. There's almost no load on those rods, so they don't fracture, they don't break. The advantages of organic solar cells are always touted that they can be rolled up in a piece of plastic, but they're made out of inherently photo-unstable materials. The advantages of inorganic materials, they work very well, but they can't be processed. So we actually have both functions in the same material. And this starts to look like one of our pieces. The second piece is going to be, or flip this over, the piece on the top. By the way, I'm sure the Bell Labs people already know the other fact, that what we did is created all the surface area, and we should be killed by all the surface recombination at all that increased surface to volume ratio. But we have a way around that, because Yves Chabal at Bell Labs shown that you could hydrogen terminate silicon and passivate it, and the only problem with that is that it oxidizes in air, and the native oxide is defective because the silicon atoms in the bulk are sp3 hybridized, and they're bonded to all the other silicons, but not at the surface. And this is a strong bond, so it terminates that, except when it oxidizes, that creates traps. So we prevent that. We'd already done that on single crystals by making a metastable surface, a chlorine-terminated surface, and then treating it with a Grignard or a methyl lithium reagent to make a silicon-carbon bond. The important thing about doing this two-step process is we can add methyl as well as ethyl, and methyl's the only group that can sterically terminate every silicon site on a 1-1-1 unreconstructed silicon surface. These have very low surface recombination velocities, less than 10 centimeters per second. They're stable in air for months. And so we can mitigate against that higher surface area because we're chemists. This is an STM image at 4 Kelvin showing that methyl termination on top of the silicon 1-1-1 lattice. We can additionally grow conductive polymers this way by seeding them with a double bond on sites that aren't filled with methyl. We have Grubbs catalysts that then can romp double bonds and get both conductive and insulated polymer sheets as the top contacts around this bottom contact. In addition, we can laminate these materials. So instead of having to grow epitaxial growth of one phase on another, we just grow a piece of plastic and grow another piece of plastic and then laminate them together like making a driver's license. The other piece of plastic is going to have the rods that are oxidatively stable, and so we've started working on that part of the problem with tungsten oxide and had some success growing those rods. Silicon's going to be below because it's a known photocathode. Tungsten oxide should be a known photoanode. It gives us 800 millivolts voltage. You need 1.2 to split water. We already have 450 from the silicon. So in principle, we should be able to put these two systems together and have a demonstration system that is, in essence, an artificial leaf because it has a membrane, It has something that reduces water to hydrogen, something oxidizes water to oxygen from a two-photon system. The membrane itself doesn't yet manage protons and electrons at the same time. Farmed that out to Paula Hammond at MIT. It's another hard problem. Here are the tungsten oxide rods. They're not oriented and felt yet. We just grew them by vapor phase synthesis to show we can get them photoactive in this form. Again, it's the nanostructured idea. Diffusion lengths are too short to make bulk materials work very well, but we just confine the geometry radially to make sure we can get them all sideways. They work. 800 millivolts open circuit voltage. So that's the N-type photoanode. Long-term stability of tungsten oxide in water is something that is debatable now, but it's very close to being stable. If we can catalyze the water oxidation just a little bit, maybe with anodic films of cobalt with phosphate, we might be able to bring us that last 9 of stability. So we're trying to see if that works. Here's rust. This is rust felt. That's a 5-micron bar. Same idea. 40 nanometer diffusion length, 3 microns to absorb the light. Here's 3 microns thick. It's an average 40 nanometer diameter. So you can see where the ideas are here. We haven't implemented them into the membrane yet, but it's pretty clear where we're going. So what is clear is, even though my friend Amory Lovin says we can save a lot of energy, that's certainly true, but you still got to make a lot of energy. In fact, no amount of saving energy ever turned on a light bulb. No amount of saving energy ever put food on somebody's table. If you save all the energy equivalent to all the energy we use, you still have to make 15 trillion watts just to hold CO2 levels to double within our lifetimes. That's the arithmetic of energy. If you want to do that, you only have 3 big cards: clean up fossil energy, build a whole lot of plutonium-containing nuclear reactors, and/or figure out a way to use our biggest resource, but it's got to be really cheap, and you got to find a way to store it too, or you don't have much. The only proven systems right now, if you're going to make a fuel, have to touch a liquid. So you have to use a semiconductor to capture and convert the sunlight. At some point, it's got to touch a liquid. And so we have to learn how to work with these semiconductor liquid junctions, whether buried or not, in order to try to put together a system that could be rolled out on this scale in this time. We still have a lot of work to do because we're working on the capture and conversion part. And if we can get even lower overpotential catalysts to deliver those electrons into chemical bonds, we would dearly love to have that and couple them in. And that's why we farmed out that harder part of the problem even to the people who have gotten ahead of us, Jonas and Dan. They will tell you about that. I'm sure Dan will in the next talk. So with that, thanks for listening, and I'm delighted to be able to tell you what we've been up to in the last year and a half.
One question.
Just one. Oh my gosh. Hey, Mark.
Do you think that there's any chance that this kind of process could be, you use a phrase you've used, cheap as paint?
I debate this with Harry Atwater. Harry Atwater, being my partner in crime in the material science applied physics system, has costed out what a CVD system would be like. He claims that glass is coated, tin oxide glass, by this same process, and that in a non-vacuum but atmospheric CVD system, that you could envision a roll-to-roll process on a piece of glass that would simply do this. I'm still, being a chemist, much more on the Paulo Lusado's side and would rather have a bucket and paint it on. So I'm not sure, because cost at scale is something, I don't know. But we are working on taking randomly oriented arrays of rods and functionalizing them both on their side and their top and seeing what it takes to get all these random things to go all pointing toward the sun, which I think is a pretty interesting self-assembly problem that we ought to be able to do. And so then you could think about other ways to make random buckets of these and then paint them on and then get them. And they don't all have to stand up like this. In fact, you really want them like grass, not aspen trees, right? So that would be the real model, right? You want all the angles. We can do a lot of interesting photonic band gap things with the periodic structures, right, which we're doing. But you really would rather not have them perfect. So maybe. I know better than to say for sure. Everybody's costs are always higher than they tell you. Right? Rule number one of industry.